Welcome to 5.04 Honors Gas Calculations. Practice number 5 in these recordings is just like the lab. These are the lesson objectives, which if you would like to read them in more detail, either pause or go to the lesson to read them. As with many lessons in chemistry, we do need to have mastery of previous material. A lot of 5.04 is writing a balanced equation, being able to use stoichiometry, and being able to use basic algebra. Please make sure that you have these skills before attempting this lab and lesson. Stoichiometry is covered in Module 4 in our course. If you did not do first semester with us, that is okay. You can go back and read the lesson. You have access to it. You can watch the recorded teaching sessions for that and come to our live tutoring if for some reason you do not have stoichiometry skills at this point. Please make sure that if you have not successfully mastered stoichiometry and the lessons in 503 and 504, please go back and do those first. You will not be able to be successful in 5.04 honors without those skills. We know from 504 the ideal gas law. It is PV equals nRT. Pressure times volume equals N, the number of moles, times R, which is the ideal gas law, times the temperature. We also know that these must be in specific units, so they cancel. Moving forward with the honors version, we also know from previous lessons in stoichiometry that molar mass, we're going to use a capital M to represent molar mass, equals the mass in grams of 1 mole of your substance. So molar mass is mass divided by mole. If we were to rearrange this formula using our basic algebra skills, we have moles. Okay, we're just going to solve for moles. So moles, which we use a lowercase n for, remember. So moles equals mass divided by the molar mass. Okay, all we did here was just rearrange to get moles out of the denominator. We solved for moles, so we get moles equals mass divided by molar mass. Now, with some simple mathematics, we can perform a few substitutions, and we can now have the ideal gas law, and where we see moles, we can substitute mass divided by molar mass. And so now we can use the ideal gas law and actually calculate or solve for the molar mass of a gas and possibly identify an unknown gas. So here's our new formula that you need to make sure you write down. PV equals M, and M is the mass in grams, RT divided by the molar mass. As with any mathematical type lesson, the easiest way to do them is to just do a problem. So what I would like for you guys to do is pause this recording, get through this problem, make your list of what you know, okay, take it out of your word problem, make a list on the left-hand side of your piece of paper of what you know. What are you given in this? What is volume? What is temperature? What is R? All those values. Write down the formulas that you know and see how far you can get in this problem. And when you've gotten as far as you can, please hit play to resume. Welcome back. So what we're going to do is we're going to make the list of what we know. Welcome back. What we are going to do is make a list of what we know. So I'm going to take all of the math, all of the numbers from this word problem and make a list on the left-hand side of my page. Okay, in this problem, it tells us that we have a volume, pressure, temperature. It gives us the mass, and then it asks for the molar mass, so we have to solve for the molar mass, and then it asks what is the likely identity of this noble gas. Okay, so I've made a list of everything that it gave me and everything that it's asking me for. Now real quick, when we're looking at our numbers and our units, we have to make sure that we have specific units. Remember, our value of R has liters, atmosphere per mole, Kelvin. We learned that when we first learned the ideal gas law. So we have to be very careful. Our temperature always has to be in Kelvin. What I recommend is that before you even start plugging things into formulas, go ahead and convert your units to the correct units so that way you don't forget. To go from Celsius to Kelvin, you just add 273. So 27 degrees Celsius is the same thing as 300 Kelvin. All right, now I'm going to write down my formula. PV equals mass times R times T divided by molar mass. And now all I'm going to do is rearrange to get my molar mass. My problem is asking me for molar mass, so I don't want to keep molar mass on my denominator. I want to rearrange this. So I get mass times R times T divided by my pressure divided by my volume. Now all I'm going to do is just substitute the values that I already know. My mass is 1.45 grams. My R and my temperature has to be in Kelvin. My pressure and my volume. And when you look at your units for R, we have liters will cancel, ATM cancels, my Kelvin cancels, and what I'm left with is grams, and then in my unit of R, moles is on the denominator. Therefore, when I finish this, my units are going to be grams per mole. And now what we're going to do is we are going to multiply everything on the top. So go ahead in your calculator and multiply everything on the top. You should get 35.7135, and then multiply the two numbers on the bottom and you should get 0.2703. And you don't have to do this. If you are good with math in your calculator, you could probably go ahead and do all this in your calculator in one step, but oftentimes we have students that need to do the top first and then the bottom, and then now take 35.7135 and divide by 0.2703. And you should get a final answer of approximately 132.1 grams per mole. Now that is our molar mass. So my molar mass is 132.1 grams per mole. The second part of this problem says, what is the likely identity of the noble gas? That's the key here. It told us it's a noble gas. So when we look at our periodic table, we go to the right-hand side because we know the noble gases are the last column on the periodic table. So when you go to the last column on your periodic table, which noble gas has a molar mass closest to 132.1? And I have a copy of the periodic table here. The noble gases are this last column: helium, neon, argon, krypton, xenon, radon. And look, xenon's pretty close, isn't it? We had a molar mass of 132.1 grams per mole. This is pretty close. So the most likely identity of our noble gas is xenon. We have worked with the ideal gas law. We've worked with the ideal gas law with molar mass. And now we're going to work with density. And we can actually substitute for density mass divided by volume. When we rearrange the ideal gas law, we can get the ideal gas law to be mass divided by volume equals PM divided by RT. With mathematics, we can perform a couple of simple substitutions, and when we get mass divided by volume, we can substitute density. So if you have the density of your gas, or you can solve for the density of your gas, and that equals P, which is still pressure, capital M, which is the molar mass, divided by R times T. Remember, temperature is always in Kelvin. Here is the formula sheet with all three of these formulas. Please make sure that you have this written down and put it in your chemistry notebook for this class. You are going to be using them in the future. Practice number 2. What is the density of a sample of sulfur dioxide gas at 0.95 atm and 63 degrees Celsius? Please pause this recording and get as far as you can with this problem. Welcome back. We are going to write down our list of what we know. Alright, so we have our list of what we know. The formula that we have that includes density is density equals pressure times the molar mass divided by R divided by T. All we're going to do is make our substitutions. So density equals the pressure, which they gave me, times the molar mass. Uh-oh, I don't have the molar mass, do I? Well, have no fear, because it told us we have sulfur dioxide gas. And at this point in chemistry, you should be able to take a name and write the formula. Sulfur dioxide means we have one sulfur and two oxygens, because those are both nonmetals. It's a covalent bond, and with covalent bonds we use the prefix to indicate how many we have. And then we look at the periodic table and we see that sulfur has a mass of 32.06. Oxygen has a molar mass of approximately 16, but I have 2 of them, so my total molar mass for sulfur dioxide is 64.06 grams per mole. Alright, so there's my molar mass. I'm going to divide by R. It has the weirdest units of everything, I know. And we multiply that by the temperature. Remember, temperature must always be in Kelvin. We have to convert 63 degrees Celsius to Kelvin. We're going to add 273. Remember, Celsius plus 273 equals your temperature in Kelvin, and that should equal 336 Kelvin. So when we multiply the top, when we multiply the bottom, 5,6. Again, I'm taking this one step at a time. Many of you guys will not need to do this step in here. You could probably just plug in this big fancy formula all at once in your calculator and get your final answer. So the density of this gas is 2.2 grams per liter. 504 Honors introduces a new concept of partial pressures. We see this whenever we have a mixture of gases. Imagine that you had a bottle and you had nitrogen gas in it, and oxygen gas, and helium gas. Well, we can actually calculate the pressure of each gas in that system. It's not too bad. We have the total pressure of the system is equal to the sum of the parts, and hopefully that makes sense. The total pressure inside a container will equal the sum of all the gases inside the container. So if you had a bottle and you had helium and oxygen, then it would be the total pressure of the bottle equals the pressure due to oxygen and the pressure due to helium. Not all gases exert the same amount of pressure. That's key for this one. Let's do a problem with Dalton's partial pressures. Go ahead and pause this recording, get through this problem as far as you can, and when you're ready to resume, hit play. Welcome back. We are going to make our list of what we know, and we're going to write down the formula. Okay, so here's our list of what we know. Our formula states that the total pressure of the system is equal to the sum of the parts. For this particular system, we have gas A, gas B, and a third gas. So I know the total pressure equals pressure of A plus B plus C. Now we're solving for PC for the third pressure. Now, depending on how you like to do algebra, you can go ahead and plug in everything in this formula, or you can go ahead and rearrange whatever is easier for you. I'm just going to plug everything right into this formula. So 2.16 equals 0.27 plus 1.58 plus PC. And then we're going to rearrange, get 0.27 and 1.58 over to the other side, and we get 0.31 ATM. So now we understand what the total pressure. This is Dalton's law of partial pressures. The total pressure of the system is equal to the sum of the parts. When you get to the lab for 504 Honors, it's not super duper clear right away what the total pressure of the system is, because sometimes, you know, how can we calculate the pressure of the different chemicals inside of a system? We can't just take helium and get the pressure of helium inside a container and then get the pressure of oxygen. So we have to find what these individual pressures are a little bit different. And that's what can make it more complicated. And what we can do is we can calculate the partial pressure of gases by doing a technique that we call water displacement. And this is exactly what you're going to do in the lab. So in the lab, when you get two chemicals together and it forms a gas, what we can do is kind of siphon or have the gas go through this tube into an inverted bottle of water, and then we bubble the gas through here. So you do your reaction, and then the gas that you form comes through here, and the gas will be pushed up top here, right? Because gases have less density than water, liquid water, therefore the gases are going to rise to the top. And eventually the gas is going to come up top here. Well, over time what will happen is as more gas is created and occupies this space, it's going to start pushing this water down and down. And then when you look at this, the water level goes down. And then what we have in this container is the gas that we formed, and we also have water vapor. Because we're collecting our gas over water, some of this water will turn into water vapor. Inside this container, you will have the gas from your reaction and water vapor. So the total pressure inside this container is equal to the pressure of the gas that you created in the reaction plus the pressure of water vapor. When you do the reaction long enough, you will get enough pressure inside here where the level of water inside the container equals the water level outside of the container. This is very important because the water level outside of the container is the atmospheric pressure. The only pressure that's pushing down right here, since it's open, is the atmosphere. Well, what is normal atmospheric pressure? It's usually right around 1 atm. And so this is the atmospheric pressure, also known as barometric pressure. It's you would have a barometer in the lab and you would just go look at it and see, okay, what is the pressure today? Whenever you watch the weather, they sometimes tell you what the barometric pressure is outside. When there's a hurricane, the barometric pressure changes. When there's storms coming, the pressure changes. So this is very important because that barometric pressure is what is the total pressure. When those two water levels are even, the pressure, the total pressure inside the container equals the total pressure outside, which all we have to do is go look at our barometer on the wall. Now in the virtual lab, of course, you're not going to physically go walk to your wall and find a barometer. But in the virtual lab, there will be a barometer there and you will just read it and you're going to record what the room pressure is. So the room pressure is what the barometer says. That's a barometric pressure, and that equals the total pressure. So when you start doing this calculation in the lab, you know what the total pressure equals. Now let's do a sample problem before we jump into a huge problem. Let's just do a basic problem just to get us warmed up and start thinking a little bit more complicated than the problems we've done in the past. So please pause this recording, read through this problem, think of Dalton's laws of partial pressures, and get as far as you can. When you're ready to resume, hit play. Okay, here's my list of what I know and what I'm looking for. This is everything that was given to me. The problem told me that I have 62 liters of nitrogen gas and that it's being collected over water that is at 40 degrees Celsius, and we have a pressure of 760 millimeters mercury. So I know my total pressure is 760 millimeters mercury. It asks me what is the partial pressure of nitrogen gas, and notice how I put as the subscript the identity of my gas. Because it told me what I have, I like to be specific when I'm making my list so I know what I have. Then it goes on to tell me that the pressure of my water, my vapor pressure of water, which is the same thing, partial pressure, vapor pressure of water, is 55.3 millimeters mercury at this temperature, which is very important because vapor pressure of water will change depending on what your temperature is. So there is a table that you can look at to find out, you know, if you're at 70 degrees Celsius, the vapor pressure of water will be different. For this problem, we just went ahead and gave it to you. So the problem is asking for the partial pressure of nitrogen. I'm going to go ahead and rearrange my formula, and now I'm just going to plug and chug. My total pressure was 760, and my pressure of water was 55.3. Be very careful with your units. They must be the same unit. They're both millimeters mercury, so I can go ahead and plug in my handy dandy calculator, and I get, now the next problem we're going to do is just like the lab. It's going to have multiple parts, and we're going to go through just as if we were doing the lab. So here is the first part. Please read the problem, make a list of what you know, and get as far as you can using everything that we've talked about so far. So I have made the list of what I was given. It told me that the mass of my potassium chlorate was 2.5 grams. We were collecting oxygen. The volume of oxygen is 290 milliliters. When I made my list, I put V, and then as a subscript I put O2 because that's the gas. The room temperature is 29 degrees Celsius, and the barometric pressure is 0.97 atm. Now remember what's important about the barometric pressure, or the room pressure. That is equal to the total pressure of your system It told me that the vapor pressure of water at 29 degrees is 0.0395 atm. And it asks me for part A, what is the partial pressure of the gaseous product? That is actually going to be oxygen. Those are the only two gases in that system. Pressure of oxygen is actually what we're solving for, so I don't know what that is yet. I know what the total pressure is. The way that water displacement works is that the water levels inside and outside of the system are equal. Total pressure inside the system is equal to your barometric pressure, your room pressure. So I know that is going to be 0.97 atm. The pressure of my water at this temperature is 0.0395 atm. Be careful, you have to have the same unit. So if for some reason your units are not the same, you must convert one so that way they're both the same unit. In the lab, you have to look up this value in the table. Alright, they will give you a table of vapor pressure. So you just find your room temperature and look up and see what the vapor pressure of water is at that temperature. And so we're going to rearrange, and we get our pressure of our gas is 0.8705 atm. That is how we calculate the partial pressure of your gaseous product. Part B says how many moles of the gaseous product were collected. We know the gaseous product is oxygen. Remember, this is all a gas. We've been talking about the ideal gas law. Pause this recording, get as far as you can on this problem, and then hit play to resume. Looking at the ideal gas law, we are going to rearrange to solve for moles. N equals PV divided by RT. This is going to be the pressure of our gas. That is what we just solved for. We're trying to find the number of moles of our oxygen gas, which is our gaseous product. We have to use the pressure of oxygen. So we're going to use the number that we just solved for. So that's pressure. The volume of our gas, remember it told us that in the problem. The volume of the gas collected is 290 milliliters. Remember the units for R equals 0.0821 liter atmosphere per mole Kelvin, which means your unit for volume must be in liters. We have to convert 290 milliliters to liters. And we do that by dividing by 1,000, and you get 0.290 liters. We'll make that a little bigger. There we go. That's the value of R. And then we're going to multiply by temperature. Now our temperature is 29 degrees Celsius, but remember, because of our unit in the value of R, we always must have our temperature in Kelvin. So that is 302 Kelvin. Remember to convert to Kelvin. You take your degrees Celsius and you add 273, and that gives you Kelvin. Alright, now what I'm going to do is I'm going to go ahead and multiply the top. When I multiply the top, I get 0.2524. When I multiply 0.0821 and 302, so I'm just going to multiply the two numbers on the bottom, I get 247942. Now I'm going to go ahead and divide those numbers, and you get 0.0102. We go back to our original problem. We cancel all the units that we can, and we're left with moles. In this problem, we have 0.0102 moles. Now what we need to do is calculate the theoretical yield of your gaseous product. The theoretical yield is how much theoretically should we have been able to make. You must use stoichiometry here. When you're calculating the theoretical yield of anything, what you do is you start off with the mass of your reactant and you convert to the moles of your product. And that will tell you how much you should have been able to make. So in this problem, we were given 2.5 grams of potassium chlorate. Stoichiometry was taught back in 4.06, 4.07. If you don't know how to set that up, please go back and review it. Go ahead and pause this recording, get as far as you can, and when you're ready to resume, hit play. Welcome back. So 2.5 grams of KClO3. When we're doing algebra and converting one unit to another, we put an X, we put a line. Whatever unit we start with, that's the unit that goes down here. Remembering our lesson 4.06, 4.07 about stoichiometry and conversions, we know that whenever we have grams, all we can do is convert to moles of that same chemical, and this is actually the molar mass. The molar mass is the mass in grams of 1 mole of your substance, and we have to look that up on the periodic table. When you add them all together, you should get approximately 122.55. Okay, our grams of KClO3 cancel. We're left with moles of KClO3. That is not our gaseous product yet, so we put an X, we put a line. Whatever unit you have on top over here, that same unit goes down here. And now when we have moles, we now can convert to moles of another chemical. So now we're going to convert to moles of oxygen. This is the only time you will have two different chemicals in the same fraction. It's mole to mole ratio, and the reason why we can do that is because this tells us the molar ratio of KClO3 to oxygen. So for every 2 KClO3s, we get 3 oxygens. Cancel the units. We have moles of oxygen left, which is what we need. So we're going to put an equal sign, and now multiply everything on the top, divide by everything on the bottom. So 2.5 times 1 times 3 divided by 122.55 divided by 2, and you should get an answer of approximately. So that is how much we should have been able to make. Theoretically speaking, that's how much we should have been able to make. For this last part, we are going to calculate the percent yield for this reaction. I had a little typo here, so I went ahead and scratched that off and put in the correct answer here for part C. Determine the percent yield. So the percent yield tells us how much of what we were supposed to be able to make did we really make. Your percent yield is kind of like a percent accuracy, if you will. Like if you took a test and it was worth 100 points and you got 80 out of the 100 points, you got an 80%, right? So your percent yield on your exam is 80%. That's what we're going to calculate here. So to calculate percent yield, we're going to have the following formula. Percent yield equals actual divided by theoretical times 100%. Our actual yield is how much we actually made in the lab. Our actual yield is how many moles of your gas that you collected. This is our actual yield. So it's 0.0102. Your theoretical yield is how much you were supposed to be able to make. Now just remember, in the lab, a lot of times things go awry. You don't always make everything you were supposed to. There's human error, there's instrument error, things like that. So when we do this, 0.0102 divided by 0.0306, multiply by 100, and you will get an answer of approximately 33.3%. In the lab, your percent yield will be close to 100%. Thank you so much. I hope you feel a little bit better about 504 honors. Don't forget about our live teaching and tutoring sessions that we have every single week. Have a great day.